So our next lecture is about rational exponents. So we want to simplify things that have roots and things that have powers. The way to do this is we're just going to use a series of properties that, if you read the text, they showed up already. So let me quickly go over some of these properties. So if you have two exponents, say a to the r and a to the s, where the base is the same, the base being a and these exponents being r and s, we've actually already seen that you can combine these together and get a to the r plus s. So you just add the exponents in this situation. If you have a to the r and then you have that entire thing to the s, then we can combine those together and have a to the r times s. So we do a multiplication of the exponents in that situation. If you have two distinct bases, a and b, and then we raise that to the r, we can actually break that up as a to the r, b to the r. Likewise, you can also go from the right to the left. So if you happen to have a to the r, b to the r, you could simplify that as a b to the r, and that also may be used in some situations. Another useful property is if you have a to the negative r, the negative essentially makes it a reciprocal, and so we have 1 over a to the r. If you happen to have a quotient, a divided by b raised to the r, then you just take the power of the numerator and the denominator separately. And over here you'll notice we're making some minor assumptions here, just so that way we're not dividing by 0, but those will pretty much be assumed automatically. If you had a to the r divided by a to the s, so here they actually have the same base. Notice the difference over here, it's a divided by b to the r. So if you have a to the r divided by a to the s, then you can rewrite that as a to the r minus s. So division becomes subtraction, and multiplication over here, multiplication becomes addition. Okay. Property 7 says if you have a to the 1 over r, then we can rewrite that as the rth root of a. So for example, a to the 1/2 would be a normal square root. And then the 8th property, which is quite useful, is if you have a to m over n, so some kind of rational, then you can write this as the nth, a to the 1 over n, and then that to the nth power, which is the same thing as the nth root of a to the m. And you could also swap the m and the 1 over n. So you have a lot of variability here. You have a lot of choices you could make in your rewriting, and in some situations one might be more preferable than the other. So let's begin with some simplifications. Now, if we want to take a square root, then what we want to do is we want to be able to find a number whose square is the number under here. So this is a normal square root. We're going to have a negative in front, but this is negative. And then can you think of a number whose square is 144? Well, that would be 12, right? Okay, since negative 12 squared is equal to negative, notice that this part is sort of in parentheses, is negative 144, okay? And notice that's different than if I took negative 12 and put that in parentheses and squared it. That would actually be positive 144. Okay, down here, can you think of the expression such that if I square it, then I would get 49a to the 10? Okay, well that would be 7a to the 5th, okay? And that's since 7a to the 5th quantity squared. Now using our properties over here, we have this multiplication. So that would be the same thing as 7 squared, a to the 5th squared, and that would be 49. And then we would multiply these exponents, so it would have a to the 10th. So that checks out. You see that the square is what we originally had, so the square root would get us to this. Now, as we progress, we'll use more and more properties to simplify these in several different ways, and you don't have to just think up what the answer is. You could actually systematically do that, especially when we see the next section. Actually, we'll have other ways that we could decompose roots, and we'll have a further list of properties. One thing I want to point out is, in some sense, you sort of will be memorizing this, but not really. It'll just become habit as you sort of do a lot of these examples. You'll just automatically use these properties without memorizing them in their general form. You'll just get used to them. Okay, so I know it looks like a long list, but you'll just with practice, you'll become familiar with these rules without having to actually cite them. You know, you will just use them. So over here, Now I'm trying to think of something whose cube root, I got to take the cube root of this. So I need to think of something that if I cube it, I will get x to the 6 y cubed. So what cubed will get me x to the 6th? So that seems to me to be x squared, because if I cube that, then I'll multiply the exponents, 2 times 3, and I'll get 6. And then what cubed will give me y cubed? Well, that should be y. Okay, and we can check that. Since x squared y cubed, now looking up here at our property list, I have two things raised to a power, so that would be each of them separately to that power, x squared cubed y cubed. And now using property 2 here, this would be x to the 6th, multiplying these two, y cubed. And that's exactly what we want to take the cube root of, so that looks like we made the correct simplification. So continuing on with our simplifications. Now let's take the fourth root of 81, a to the 24th, b to the 8th. So now we have to think of something whose fourth power would give us what's under this fourth root. So could you think of something that we raise to the fourth power and get 81? Well, you could probably think of something squared gives you 81, which would be 9, right? 9 squared gives you 81. But 3 squared gives us 9. So that, to me, seems like 3 to the 4th should probably be the correct thing. So we'll continue and show this. Again, I'm going to show you other ways to simplify this, but right now the basic definition that we have when we're taking this root is you got to think of something that is raised to that root power will give you back what's under the root. And here it looks like a to the 6th will work, because 6 times 4 will give me 24, and b squared should work. Okay, so let's see if this works. So since 3a to the 6th b squared raised to the fourth power. Now if you come up here to this list of properties, it looks like we're only using these things with pairs, but even if you have more than that pair, it'll still be a valid property. So even though I have 3 separate things here, this is 3 to the 4th, a to the 6th, a to the 6th to the 4th, and then b squared to the 4th. So that would give us 3 to the 4th, which you could write that as 3 squared squared, or you could just compute that as 81. And then this would be a to the 24th multiplying the exponents, and then this would be b to the 8th. And the only reason I'm writing this, just so you could see, that's 9 squared, a to the 24th, b to the 8th, and 9 squared is 81. So 81, a to the 24th, b to the 8th. And that checks out, right? That's exactly what we wanted to take the fourth root of. And so this is our answer, right? I guess I should have boxed these as we went along, right? But I think you see how the definition works here. Okay, now let's convert the following radicals to expressions with rational exponents and simplify where possible, and assume all variables represent non-negative numbers. Okay, so if you have to take the 8th root of y to the 4th, this last property here, property 8, allows us to kind of rewrite roots, and our expression kind of looks like this right here. So we're always going to be able to rewrite such things as follows. So do you see that this is y to the 4th? So the numerator of the fraction that you write will be the power, and the denominator will give you the root. So that'll be 4 over 8. And we should reduce this, since 4 divided by 8 is actually 1/2. We should write that as 1/2. Okay, so convert the radicals to expressions with rational exponents. Okay, so we want an answer in the end to be a rational exponent and simplify. So that would be our answer. Okay, even though that this is actually equivalent to the square root of y. So the next one here, we are going to rewrite this as y squared. Numerator will be the power divided by, and the denominator will be the root. So divided by 10. Okay, again, we're using property 8 above, and reducing this, we could write this as 1 over 5, which is also the same thing as actually the 5th root of y. Okay. So our next problem is to convert convert to the appropriate root. Had an extra the there. Okay, so convert the following to the appropriate root and then simplify. So 49 to the 1/2, using property 8 above, the denominator becomes the root. So you could write this, the 2th root of 49, but we reserve that second root as just without writing anything, okay? So normally, if you had a to the, remember up above, you have a to the 1 over n, this is the nth root of a. But if you happen to have a square, 1/2, then the square root is the one that we don't designate there. Okay, so now what number, what is this? The square root of 49 is 7, because 7 squared is 49. So this would be the answer. 81 to the 1/4 would be the 4th root of 81, and we actually figured that out in that previous problem, right? This is actually 3, since 3 to the 4th is 81. So 3 to the 4th is 3 squared squared. 3 squared is 9. 9 squared is 81. So that checks out. We already saw that. Now what about this? We have a fraction, 8 over 27 to the 1/3. So we can write this, well, you can actually write this 2 different ways, but using the properties up above, we actually have that this is 8 to the 1/3 divided by 27 to the 1/3. Okay? If you have a fraction raised to a power, you can raise the numerator to that power divided by the denominator raised to that power. And now converting each of these, the numerator would be the cube root of 8 divided by the cube root of 27. Okay? The cube root of 8 is 2, because 2 cubed is 8. 2 times 2 times 2 is 8. And the cube root of 27 is 3. 3 times 3 is 9, times 3 is 27. So that would be 2/3. Okay? Your calculators, if you're using a scientific calculator or something else, usually there is there's usually a square root button. A lot of times there's a cube root button, but you also see a sort of an nth root button, and you would specify what root you're actually doing, and you can actually calculate these things using that. But here, we haven't specifically needed a calculator. You should try to solve these without using that assistance, because it's good practice, but that's how you would do it. And then for these problems down here, we just want to simplify that. So 9 to the 3/2. Well, how can we rewrite that so we can finish this? Well, the numerator, whenever you have a fractional power, that is the power of. Okay, so we could do this 2 different ways. I actually know how to take the square root of 9. So the denominator, you see that I could write this as 9 to the 1 over 2 cubed, right? That's one of the ways that I could decompose this. 3 times a half is 3/2. But I know how to take this. This is actually the square root of 9 cubed. And then the square root of 9 is 3. And then 3 cubed is 3 times 3 times 3, which is 27. Okay? What about this one here? If you have a negative power, then we know that that's 1 over the same thing but with a positive power. Okay? And what do we know about 4? Well, we know how to take the square root of that, so it seems like a good strategy to write this as 4 to the 1/2 cubed. And that's 1 over the square root of 4 cubed. And that's 1 over 2 cubed. And that's 1 over 2 times 2 times 2, which is 8, so 1 over 8. How about this one here? So this one, we have x to the 3/4 times x to the 5/4. Well, we have a property that when we have the same base and we're multiplying things like this, then we would add the exponent. So we have x to the 3/4 plus 5/4. And when you're adding fractions, they have the same denominator already. You just add the numerators and divide by the same denominator. So we have x to the 8 over 4. And we can do some reduction, right? So 8 over 4 is just 2, so this is actually x squared. And then this one here, if we have a ratio, x to the 2/7 divided by x to the 5/7, then that converts to x to the, we have the same base there, so it's x to the 2/7 minus 5/7, so we actually subtract them. And we can simplify this, so this would be x to the negative 3/7. And I mean, you could rewrite that several different ways, but I don't think we're going to get anything simpler than this because 3 and 7 don't have any common factors. So that's one way to write it. I suppose another way that you could write this that would be acceptable is 1 over x to the 3/7 that's fine by me as well, or any of the other equivalent things that you could have written. All right. Usually you only want to simplify things if it's actually going to make it easier for you to use it in some way. Okay, but that's how we do these kinds of things.